Okay, so the next notion we want to discuss is the notion of a subspace, more precisely a vector subspace. I forgot to mention that vector spaces are also called linear spaces. You'll see that terminology as well. And then it would be called a linear subspace. It's the same thing. It's just equivalent terms. So what is a vector subspace? So let's write the definition. So let V be a vector space. W, which is contained in V, remember this symbol for being contained or equal to, okay? So when I write this, I just mean that they're contained as sets. So here is V. Let's say V is all the elements sitting here in this big pile here. Do you see the pile? Okay. Now there's a structure. We can add them. We can multiply by a scalar. But basically, the first thing they are is just a set of elements, right? So W is just part of them. We take only part of them, not all of them, part of them. Maybe all of them, but not necessarily, okay? If we take a subset, that's the notion of a subset. Take part of the elements. Let V be a vector space. W in V is called a vector subspace or a linear subspace if W is not just a partial collection of elements, but those elements in W themselves form a vector space. Okay? If W is itself a vector space. And not just any vector space, with respect to the operations from V. So it's not just a vector space with respect to some new operations that you define, but you take some of the elements and they happen to be a vector space on their own with respect to the operations in the bigger world they're living in. Okay? So before we even decipher this more carefully, let's do some examples, some very trivial examples. So examples. So here's example 1. Polynomials of degree less than or equal to n, less than or equal to, not equal to, but less than or equal to n. Let's write it like this. Let's do this. W is going to be the polynomials of degree less than or equal to n, and V is going to be, remember how we denoted polynomials? We said f for the field, f of x. Those were the polynomials, all the polynomials. Okay? So this is example 1. So we already said that if you look at all the polynomials, they form a vector space with respect to addition of functions, addition of polynomials, and multiplying by a scalar. Okay? Now you take only the polynomials of degree less than or equal to, let's say, 7. Are they, first of all, are they contained in all the polynomials? Obviously, yes. Are they themselves a vector space with respect to the same operations? And the answer is now yes. So many of the properties follow. For example, the fact that if you take two polynomials of degree less than 7 and add them, f plus g or g plus f, you get the same thing. That follows automatically from the fact that it holds here, right? Do you agree? But some things don't. For example, you have to verify that W is closed. That if you add two folks in W, you know that you're going to get a polynomial, but is that polynomial going to be in W? And the answer is yes. If you take two polynomials of degree less than 7 and add them, their sum is also going to be of degree less than or equal to 7. Do you agree? Okay? Good? And you need to trace all the properties. Okay? Is the 0 polynomial here? Yeah, because we're taking polynomials of degree less than or equal to 7. Does every polynomial have an inverse here inside W? Yeah, right? If you take the a polynomial of degree less than or equal to 7, I'm saying 7 rather than n just to make it less abstract, but it's, of course, you can just say n. Its inverse, which is just putting minuses on all the coefficients, is also going to be of degree less than or equal to 7. Do you agree? So you need to verify each of the properties and agree that this set W, which is a subset of V, it's not all the polynomials, it's only some of them, but it's again a vector space with respect to the same operations. Good? Is the idea clear of what a vector space is? Okay, let's do some more examples. Example number 2. W is going to be functions that satisfy that their value at 1 equals 0. And V is going to be all the functions. Let's say real valued functions. W, well, if you look at all the functions, clearly if you take only those functions whose value at 1 happens to be 0, it's a subset. You didn't take all of them, you took some of them. Right? Do you agree? So do you agree that W is contained in V as sets? It's some of the functions, right? Is W a vector space? You have to start tracing all the axioms and checking if they hold. Is the 0 function in W, for example? Yeah, because the 0 function satisfies that its value at 1 is 0 because its value at every point is 0. Do you agree? So the 0 function is in W. When you add two functions, think of the graphs. When you add two functions whose value at 1 is precisely 0, the sum of the functions, the value at 1 is going to be 0. Do you agree? Okay. When you add f satisfying this and g satisfying this, does it matter if you add f plus g or g plus f? Doesn't matter, right? That, by the way, again, let me remark, it follows automatically since it holds here, right? It's really redundant to check some of the properties again for W because they follow for free, right? Because if two elements commute in the bigger space, of course they're going to commute in the smaller space. That can't change, right? Only some of the properties can change. For example, having 0 can change. If you didn't take 0, it's not there. It's not a subspace. Do you agree? If it's not closed, it's not going to be a subspace. Okay? We're going to have a theorem of that sort in a minute, that you don't really need to check to verify all 10 axioms, that in fact it's sufficient to verify 2.5 of them. Okay? We'll have a theorem of that sort in a minute.
That's basing on that W is actually a subspace.
No, you start with W, which is a subset.
Oh, so that satisfies it.
Okay? Being a subset just means that it's some elements from here. And you want to verify that it satisfies the axioms of being a space, a vector space. And what I'm saying is that some of the axioms are going to be satisfied automatically for free. You don't really need to check them. Okay? But some are not. Okay? We're going to say that more formally in a minute as a theorem.
But I have to accept as that when I'm given that W is a subset of V, it's given to me, right?
No, that's the first thing you have to check, that it's a subset. Okay, let's do more examples. Wait, good question. Wait, let's do some more examples. You're going to see in more examples an answer to your question. That's a good question. So do you agree that Rn is a subspace of Rn? In fact, the entire V is always a subspace of itself. Do you agree? Everybody? Clearly it's a subset. It's called a trivial subset. It's everything. And it satisfies all the axioms, the same axioms, because it's the same thing. Okay? So this is true in general. Suppose I take the empty set. The empty set. I take nothing. Is it going to be a subspace? The board you should be looking at is the one over here, which we left from the previous video, where you have all the axioms. Suppose you take the empty sets, no elements. Is it going to satisfy, is it going to be a subspace?
No, because there is no zero.
Right. For example, 0 is not there, so it can't be a space. A space has to have a 0 element. If you took the empty set, that's it. It doesn't have the 0 element, so it's not a subspace. Do you agree? Okay. But if you take only 0, you take the set that contains only 0. That's the only element you pull out of the pile. Okay, we're back on this board. You take only 0, this is a subspace of any v. Why? Why? Well, you have to trace all the axioms. Well, the easiest one is to see that 0 is there, because we took it, right? But is it true that 1 times v equals v for any v here? Yeah, because the only v here is 0, and 1 times 0 is 0, right? Is it true that when you add 2 elements here, it doesn't matter in which order you add them? Yeah, because 0 plus 0 equals 0 plus 0 in either direction, right? Is it closed? When you add 2 elements from here, do you get an element here? Yeah, because the only things you can add is 0 in itself, and you get 0 and it's here, right? So 0 is a subspace. Both of these subspaces are called trivial subspaces. One is trivial because it's the smallest one, and the other is trivial because it's the biggest one. Okay? More examples. Let's continue here. Let's look at W, all vectors of the form x, 0, 0, where x is in R. This is obviously contained in R3 as a set. Do you agree?
Yeah.
Okay. Is it a subspace?
Yeah.
Okay. Look at what's written here. Do you see that there's some notation to struggle through if you're not used to it yet, right? This is the set of all 3 tuples that have 0 in their second and third coordinate and any real number in the first one. Okay. And it's a subset in the set of all 3 tuples, R3. Do you agree? Now the question is it a subspace? Okay, so what do you need to check? You need to check all the axioms. Is the 0 vector here?
Yeah.
Yeah, when x is 0, you get the 0 vector. When you add 2 dudes like this, do you get somebody like this? Yeah. Do you see that? Okay, you're never going to get anything other than 0 in the second and third coordinates, right? When you multiply somebody like this by a scalar, by 5, do you get somebody like this? Yeah. Okay, so you need to verify that indeed this is a subspace. Okay, you need to go through all the axioms and verify that it's indeed true. Okay, here's another example. By the way, what is this geometrically? Remember that R3 is just 3-dimensional space. What is this geometrically?
It's the vector and the x-axis.
Right, it's just the x-axis sitting in 3-dimensional space. Okay, so another example of this sort, all the guys of the form xy0. Oops. xy0, where x and y are in R, is a subspace of R3. For the same reason, and what is this? This is the xy plane sitting in 3-dimensional space. Do you see that? Geometrically. Okay. How about this? W is going to be R2, and V is going to be R3. Is R2 is 2-dimensional space. Is it a subspace of R3, 3-dimensional space?
Yeah, that's what we just proved.
Just like the x.
Good, you're all wrong. Okay, this is not the same as 6. 6 is taking 3 tuples and forcing the third coordinate to be 0. Okay, this is indeed a subspace. This is not a subspace for the very basic reason that this is not a subset. Elements here only have 2 entries. These are elements of the form AB, and these are elements of the form ABC. If you stick your hand to the pile that contains all the elements of the form ABC, you're never going to pull out an element like this. It's not even a subset. Okay? If you want to think geometrically of the plane as a subset of three-dimensional space, this is the way to do it. Not this. Okay? Not even a subset. Good? Example 8. Let's look at W is going to be all the vectors x, y, z, where x, y, and z are integers. Not real numbers, but only the integers. All the entries have to be whole numbers. Is it a subspace of R3? Of three-dimensional, it's a lattice. It's all the points that have integer entries. Okay? Is it a subspace? Is it a subspace?
Above.
Is 0 there? Yeah, 0 is good. If you add two guys like this, do you get if you add two vectors with only integer entries, do you get a vector with integer entries? Yeah?
Not closed by multiplying on the scala.
Very good. It's not a subspace of R3 because it's not closed by multiplication by a scalar. If you take 1/2 times a guy like this, and you can because we're working with the same operation from the parent space, okay? That it inherits from the parent space. So the field is R, okay? The field is R. You can take the scalar 1/2 and multiply it by a vector here, but the product is no longer going to be here. There's no closure under scalar multiplication. Not a subspace of R3 since not closed under scalar multiplication. Good?
But if it was above integer, the integer space, it was okay?
No, because, so the question is, suppose we take not R3, but Z3. So Z3 is not a vector space to start with. Not even over Z, because Z is not a field. Vector spaces are defined where the underlying world of scalars is a field. That's in the definition of a vector space. So if you look at this and for what you're asking, is this a space in its own right? Is this a space in its own right? Not as a subspace of R3, because we saw that it isn't, but in its own right. Is this a vector space? The answer is no, by definition, because the scalars are not from a field. Z is not a field. There are no multiplicative inverses in Z. Okay, so by definition, this is not a vector space. Okay, let's see some more examples, slightly more sophisticated, and in fact very useful ones. We're going to use subspaces a whole lot. So here are a couple more examples. Let's look. What number are we on? 9. Let's look at W is going to be all the x, y, z's such that x plus 2y minus z equals 0. Obviously, this is contained in R3, right? But it's putting some restriction on the entries, some more complicated restriction. Is it a subspace? Is it a subspace? So we need to verify all the axioms. We already feel by now that some of them we don't need to verify. For example, if we take two of these and add them, it doesn't matter if we add them like this or like this, right? So commutativity is going to hold for free. We don't need to check it. Do you agree? Okay. What we do need to check, for example, is the 0 vector here. Does the 0 vector satisfy this? Yes. So do you agree that 0 belongs to W? Right? Suppose we take two guys in W and add them. is the sum going to be in W?
Yeah.
Looks like it, right? How do we write it? How do we formalize it? Well, let's do it. So suppose we take x, y, z plus, take another one, let's call it x prime, y prime, z prime, and both of them are in W, okay? What we want to verify is that the result is in W. So this is going to give us the vector x plus x prime, y plus y prime, z plus z prime. Do you agree?
Yeah.
This is in W. That's our assumption. This is in W. We need to check, is this in W? That would mean that W is closed under addition. Okay? So how do we check this? We have to check that the entries of this vector satisfy the constraint which means to be in W. Okay, so let's do it. So this is indeed true because x plus x prime plus 2y plus y prime minus z plus z prime, that's what we need to take, right? This is the first entry plus 2 times the second entry minus the third entry. If this is 0, then it's in W. Do you agree?
Yeah.
And it is 0 because these are now numbers from R. These are elements from the field, right? So we can rewrite this as x plus 2y minus z plus x prime plus 2y prime minus z prime. This is the same thing. This is 0 because this one was in W. This is 0 because this one was in W. And therefore, this whole thing is 0. So we can replace this question mark by yup. Good. Let's check that it's closed under scalar multiplication. So suppose we take alpha times x, y, z. Oops. Alpha times x, y, z. We get alpha x, alpha y, alpha z. Is this in W? And the answer is yes, from a very similar argument, right? So this belongs to W, indeed, since alpha x plus 2 times alpha y minus alpha z is 0 because it equals alpha x plus 2y minus z, and this is 0. Good? So this is how we formally verify these 3 conditions. You still need to verify the other 7 conditions, but that's going to be our next theorem. You don't. In fact, these are the only 3 conditions that you need in order to verify that a subset is a subspace. All the other conditions follow for free. So let's write that as a theorem.
They follow the 3 only if we know that it's a subset.
That it's a subset. If you take a subset, then you only need to verify 3 axioms, and there are versions of this theorem. In one you need to verify 3, in the other you need to verify 2.5. Let's write that. So theorem W, if W is not empty, if it's empty,
It doesn't have the 0.
it doesn't have the 0. It can't be a subspace. So if you take a non-empty subset of V, so W of V, V is a vector space. Okay, V is a vector space. W is a non-empty subset of V. Okay, can you read through the notations and abbreviations? Okay, so W is a subspace if and only if W is closed under addition and multiplication by a scalar. Okay, so these are the 2 properties that you need to check. And the half property is you have to verify that you didn't take the empty set. Okay, let's prove this. Okay, if we want to claim that such a statement is true, we better be able to prove it. Okay? We already have the intuition from all the examples that we did that it really should suffice. Okay? So, first of all, do you agree that there are two directions to prove? Right? We need to prove that one direction is, if it's a subspace, it satisfies these two. So this direction is obvious. Of course. Because being a subspace means satisfying these two plus 8 more, right? So of course, if it's a subspace, it in particular satisfies these two, by definition, okay? By definition. What about the other direction? So the other direction is the tricky one. You only know these two. You need to show that it is a subspace, okay? So the first thing I want to show is that 0 is there, because we already have a feeling that 0 is essential. If it's not there, something's wrong. So all I know is that it's closed under addition and multiplication. Let's show that 0 is there. So 0 equals 0 v for any vector, right? Let's not write v. Let's write w. Okay? Do you agree to this? This is a property in the bigger space. We proved this, that when you take 0 times any vector, you get 0. Do you agree? But if it's closed under scalar multiplication, then this is in W. Therefore, 0 is in W. Since W is closed under scalar multiplication. Once again, you take an element W in W, any element you want. There is one at least because it's not empty. You multiply it by the scalar 0. Okay? You get 0. That we know from the bigger space, from V. Do you agree? But since W is closed under scalar multiplication, whatever you got here is going to be in W, because it's closed under scalar multiplication. So 0 is in W. Good? Bit confusing. There's almost nothing to write, but there it is. Okay, so some of you are looking at me with some puzzled looks. So ask a bit later, because we really are short in time. Okay, so let me just finish this proof. The other thing I want to show is that minus W is in W for any element. So minus W is minus 1 times W. Do you agree? This you also had to show. I left it as an exercise. Okay, so, and this belongs to W for the same reason. So inverses are there too. Okay, so 0 is there, inverses are there, and all the other properties and all other axioms follow automatically from V, from the parent vector space, from the ambient vector space. Okay, and the reason is that what we kept saying, right? If you add two guys, you have to check that W1 plus W2 is again equals W2 plus W1. But you know that because they live in V and it's satisfied in V, so it's still going to be true. And you have to check all these distributivity properties and the associativity of addition, and all of those follow for free from V. So the only things that really need verifying are 0 and the inverses, and they follow from this. Okay? So now we know that if you want to check if a subset is a subspace, all you need to check is that it's not empty. And by the way, usually the way we check that it's not empty is check if 0 is there. That's usually the easiest thing to do. That's why it's sometimes considered as 3 things. Check if 0 is there. That would tell you that it's not empty. Okay? And check the closure properties. If they hold, that's it. Okay? We're going to continue this discussion next time we're short in time. We need to stop now. We're going to continue this discussion next time and discuss more properties of spaces and subspaces and how we form subspaces. And of course, a bit later, how all this relates to things that we're interested in. Like, for example, solving equations, for example. Okay, so that's it for now.